on theory and databases, and today we will continue with theory and AI. And I give Van den Broeck, and Yu Jung Choi will give the 4 lectures. Please.
All right. Thanks everyone for being here. So we have 4 hours of material to teach you everything we know about logic and probabilistic circuits, which arguably may be less than what some of you know about some of these topics. And so, because it's the start of the program, please just interrupt and ask us about something we're forgetting to mention, or I'll give you the outline soon, but if we make it through half of this, I'll already be happy. We'll just find the most interesting parts for you. Okay. So logic and probabilistic circuits. So the main idea is that circuit representations are somehow a nice language to capture tractable reasoning in logic and probability at the same time. And most of you are logicians, so you've probably seen circuits in that context. And so even though logic is central to this Simon's program, this tutorial will actually mostly talk about probability for a few reasons. One is, we more do probability than logic, so it's easier for us. But second, I think most of the interest in the database and the AI community in logical circuits for the last 15 years or so has been as a means of doing probabilistic inference, as a way to compile your probabilistic model into some data structure or logical circuit where you can then do probabilistic reasoning. So in a sense, it matches well the actual goal that people have. One of the things I hope to convince you of in today's tutorials is that once you think about probability, there's very nice, rich query languages you can define. Maybe that wouldn't be natural to define in logic. And so hopefully this will be interesting for you to study from a algorithms point of view or a complexity point of view. And then lastly, AI and the world is going through a crazy time. We're in the age of generative AI. And so generative AI is all about sampling from probability distributions. And so hopefully the way that we present circuits to you today will help you also connect things like circuit compilation, inference on circuits and circuit lower bounds and so on to this world of generative AI and deep learning. Okay. I do recognize that we're not really here to talk about machine learning, so I will spare you most of the machine learning details, except where I maybe connect to some kind of machine learning models, deep learning architectures. And we'll mostly talk about representations, query languages, reasoning algorithms, and some connections to theory, to generating polynomials, to circuit lower bounds, and so on. Okay. All right, so this is on the menu for today. I will start giving you a very gentle introduction, hopefully, to the world of probabilistic models in AI and machine learning. And I'll try to define what are some interesting probabilistic queries you may want to compute on these models. And we'll discuss for most of the popular ones whether they're tractable models or whether they're intractable for computing these types of queries. And then second, I'll talk about probabilistic circuits, which is this convenient framework, this kind of circuit language framework, where it's pretty easy to analyze for different query languages whether they're efficient to compute or not. And so this will hopefully connect to your knowledge of tractability and logic and so on. And so then Yu Jung takes over, and she'll tell you about what is the connection to logical circuits, binary decision diagrams, SDDs, DDNNFs, all of those kind of classic logical representations, and show that they are really very much the same thing in a way. And most of the probabilistic models we use are actually inspired in very direct ways by what people have done in the logic circuit world. Then Yu Jung will tell you how do you take your favorite other model and compile it into a circuit. We'll talk about the circuit size, lower bounds, tractability, how it relates to circuit size, and so on. And then Yu Jung will try to impress you by giving you some query languages that you would imagine could never be computed efficiently, and then still show you that they can be computed efficiently if you have the right model, the right circuit language. And so this will hopefully be exciting for database folks who love query languages that get as fancy as they get, right? Okay, so then I take over again, and so this will be later in the afternoon, and I'm very eager to tell you or to discuss this question: are all tractable distributions actually circuits? Is this somehow a universal language for all things that can be efficiently computed? And so I would like to give you some interesting recent results in that direction. And then finally, what I hope we won't have time for is to actually tell you how the machine learning side of all of this works, how you train these things on the GPU from massive amounts of data, because I don't think anyone here is particularly interested in that topic, but I could cover it if you're curious, or I can give you the high-level story. Okay, and again, if we, just tell me what you care about, or even if it's not on this slide, and I will hopefully tell you, right? So let's make this interactive. I will force Dan to ask some questions later. Okay, I should acknowledge that the slides we use are based on tutorials and slides from other people. So thanks to all these folks for all the hard work they did. And so let's get started. So here we see some alphabet soup of probabilistic models in AI. You could make a similar slide for logical representations in AI. And so here there's a bunch of things that look familiar, things like the naive Bayes distribution you've probably seen at some point, tree-shaped graphical models. On the side here is GPT, transformers, right? ChatGPT, GPT-4, etc. There are some really famous models like variational autoencoders, generative adversarial networks are somewhere in this soup. And so these are all probabilistic models that define somehow a distribution or a way to sample new things from the world, okay? And it's a bit confusing to make sense of this soup. And so the way that we will put some structure here is to say that a bunch of them are tractable, the ones over there. These are ones where there are certain query classes that I can compute efficiently on this representation. And then there's a bunch of other things that are intractable, where they really don't allow you to compute things exactly and efficiently on the even though they represent a distribution. But of course, it's a little bit more subtle than that. It's not just tractable versus intractable. We'll talk about the spectrum of tractability, where depending on the query language you have, you might have a tractable model. Some models are tractable for almost any question you ask. Some models are tractable for nothing, and some are tractable for only a few types of query classes you might have. And I'll try to make this concrete soon. Okay, then there's a second orthogonal dimension, which is also really important, which is how expressive are these models. And so we know that, for example, a transformer is very, very expressive. It can somehow capture all text on the internet and all human language behavior quite well. On the other hand, the naive Bayes model is very naive. It's so naive that they had to put it in the name just to make it clear. And so what we would like, of course, is we would like an expressive model, especially among the ones that are tractable, that can still represent very, very complex distributions while still being tractable. Okay, and then the final takeaway that we'll get to in my part, the first two parts of this tutorial, is how do we make sense of this alphabet soup? I don't really want to explain to you all of these different models. It turns out that they're really almost all the same thing. You can really think of them as just circuits in some syntax, and they all have similar properties. And I'll try to just give you the essence of these things. And once you know this framework of probabilistic circuits, all of these things are really just different syntax for the same kind of model. So hopefully you will understand all of this without having to study them individually. Okay, any questions at this point? No? Okay. So let's get started with tractable inference, query classes, and so on. And so this is a type of slide that I mostly use to explain when I teach this to machine learners, what is a query, right? Because people don't actually know what a query is for example, in machine learning. But for you, this is very natural. But okay, let's indulge anyway and talk about queries. What are queries? So here's a query that I might ask. What's the probability that today is a Monday and there's a traffic jam on Westwood Boulevard? So we're going to translate these intuitive queries to random variables. So there's a distribution here over the day of the week, the time, whether there's a traffic jam in all the streets of Los Angeles. And so this query here specifically is asking, in my distribution over however the traffic in Los Angeles behaves, what's the probability that it's a Monday and there's a traffic jam on Westwood Boulevard? Okay, so this is what you would call a marginal query, and this will be the almost simplest type of query that we're going to consider today. There will be many much more complicated ones. Here's another query. Which day is most likely to have a traffic jam on my route to campus? So again, we assume that our model is the same probability distribution over these random variables. And now we would like to ask, what's the day that most likely has a traffic jam in any one of these streets that are on my route to campus. Okay, so this is a little bit more complicated. It uses some features of the query language, like map inference, what's the most likely day. It uses some event that is not just there is a traffic jam on Westwood Boulevard, but some logical event, something that you specify as a sentence in logic. And it also, of course, uses marginalization because it doesn't really talk about the other streets and so on and so on. Okay, so this will be a bit more complicated, and so Eugen will tell you how to deal with these types of more advanced queries. Okay, so what do we mean when we say tractable? And this hopefully is kind of intuitive for you, right? You've probably already figured this out. So a class of queries is tractable on some family of models if essentially the query, any query in this class runs in time polynomial in the size of the model. And so size of the model is, of course, a bit arbitrarily defined, but because we'll be dealing with circuits, this will always be the number of edges in the circuit. Okay. And for almost all of the query classes we'll talk about, a polynomial will actually be linear, which is very important if you want to make this practical and actually plug this into some machine learning pipeline and so on, right? So we're not going to do things that are, you know, size of m to the power 1000. It's going to be linear in the size of the circuit.
Just to be clear, the way you stated the problem could be combined complexity or data complexity, but you actually have in mind data complexity for every fixed query.
Yeah. So from a database perspective, the model is the database, I guess, and then this is data complexity. Yes.
Thank you.
Typically, the queries. So it gets more complicated when the query becomes, let's say, a logical event, which also has a very rich structure. Then you want to be polynomial both in the size of your probabilistic model and the size of your query written as a logical sentence. So that's a more advanced definition, and so Eugen will get into those types of queries. But for now, the queries will be very simple. There's nothing interesting in their structure. Okay, so let's do this exercise where we figure out for a bunch of models and a bunch of query classes whether they're tractable. And let's start with the very, very simplest one. So here is a query. Yeah, question?
Because you talk about probabilistic model, can you define what is a probabilistic model?
Any joint probability distribution over these random variables. So a Bayesian network, whatever, like a variational autoencoder, a transformer, GPT.
Okay, but it's a joint distribution over
any joint distribution over these random variables, yeah. So we'll look at some specific representations in just a second. Okay. Here's our very, very simplest query. Complete evidence or likelihoods. So this is asking, what's the probability that today is a Monday? It's exactly 12. There's a traffic jam on Westwood Boulevard and nowhere else. So basically, you fix all of the random variables values. You leave nothing unknown. And now you want to compute this probability. Okay. So the reason why we care about this type of query is because this is very fundamental in maximum likelihood learning. When we're given data, whatever text from the internet, images, we do have a value for every pixel. We do know which token is in every sentence. So when we train these models, we want to be able to compute queries in this class and then maximize the likelihood, meaning find those parameters that make this number higher. Okay. It's not really a type of query that you would, as a user, necessarily want to ask, except when you're maybe doing things like outlier detection. But it's very important as part of the learning loop. Okay, so let's take our favorite generative model from 5 years ago, the generative adversarial network, right? So I don't know how many tens of thousands of papers have been written about this specific representation of a probability distribution. I'll spare you the machine learning details. You can ask if you really care. But essentially what this is doing is it's defining some way of first generating, let's say, fake images, and then training a model to detect which ones are fake and which ones are real, and then somehow having them compete so that you start generating images that are more and more realistic. So this model doesn't have an explicit likelihood. It's being trained in this way where you have these two neural networks kind of trying to beat each other at some game. And so there's no way to actually compute a likelihood. You cannot ask these models, what's the probability of this specific image? There's no way to do that. There's reasons why people care or don't care about these architectures, but bottom line is, so this is already a model class that is intractable for even the simplest query, which is the likelihood. All right, so this was a little warm-up, exercise. So let's look at the second favorite deep learning model for probability distributions, the variational autoencoder. This one I find a bit more interesting. It's a latent variable model. It's saying that there's some kind of embedding space where you have a distribution, and if you take some embedding, you can decode it into an image, let's say, and then there's a clever way to actually get a posterior on Z and so on and so on. But all of this machinery, which I suppose you don't care about, so I don't have to tell you, this is also kind of using approximations, lower bounds, to estimate what roughly would be the likelihood of a particular image, the likelihood of the model for a particular image. And so again, computing this is intractable, and it's also something that does not support this class of queries.
I have a question about why these are intractable later on, because like the structure of how it represents something.
Yeah, so that's somehow hidden in here. If you want to compute the probability of an image, you have to essentially integrate over all possible continuous vectors that could possibly, every single vector could possibly generate every possible image. So you have to kind of do this integration where you say, for a given image, what's the probability of every single infinitely many, uncountably many embedding to generate it? That integral is just completely intractable.
Everything is connected to everything. You can't exploit some structure and some.
There's no structure here whatsoever. Yeah, exactly. So I won't really talk about it much more. I'm just trying to dismiss these models as not really interesting for the purpose of querying, as like a database person would think of it. Yeah.
Should we understand this as there is a proof of intractability, or we just don't know how to do it?
It's very easy to prove. I'll do it in the break. Yeah, it's very simple because even just, let's say that this was a uniform distribution, this was just a sigmoid, it's already a Sharpie heart. So very easy. Okay. All right, so let's look at our next machine learning model. So here it says normalizing flows. These are very popular with machine learners. You've probably never heard of them. So they are kind of telling us that what we really need is a distribution over some Z variable that we don't know, some latent variable. And then for every Z, we will map it to an X using a bijection. And because we have a bijection, there's actually this change of volume term here. We can actually compute for a particular image, if we invert this function, what's the probability of Z? And then also how much does our function actually blow up or shrink the volume in this particular area of the space? Don't worry about it. It's a bunch of machine learning stuff. But it kind of explains why a lot of neural networks are actually able to compute the likelihoods. Okay, so these are models where we can compute indeed the probability of a specific image. So that's something. Okay, we have finally a model that's tractable for a particular query. All right, so that's success. So let's make the problem harder. Okay, so let's look at these marginal queries that I mentioned a while ago. So marginal query looks like this. It's kind of like this probability, this EVI, this likelihood query, where we deleted a bunch of information. So now we have to reason about whatever values could be there. Okay, so this is what it looks like. And you can think of these, of course, as just integrating out all of the hidden or the latent variables from this distribution, where all of the hidden variables are just all the variables that are not observed, which are the X variables. Okay, hope this makes sense. And a very related problem is computing conditional probabilities, because if you can compute a marginal probability, you can also compute a conditional probability, as we all know. All right. This is quite useful as a problem. So throughout the tutorial, we'll have a few pointers to like application slides to tell you this is useful in robotics or computer vision and so on. So you can be motivated as you prove your theorems that people might like to use your theorem in some application. So let's go back to our normalizing flows. We kind of like them because we can compute the probability of a complete image, a complete feature vector. But unfortunately, computing marginals is again intractable. Now we have to compute some integral over this thing, and unless this function is super trivial, this is very easy to prove also to be intractable. Okay. So if I have a normalizing flow model and I have an image where I maybe don't observe the right half of the image, I would never know how likely the left half is of the image. It's impossible. All right. So flows, a little bit tractable, but not really. Okay, so let's go back in our time machine before the deep learning revolution, and let's look at graphical models, things like Bayesian networks. Question?
So, when here we talk about the tractability, you mean exact computation of the
Yes.
probability, right?
Yeah.
So, are we talking about approximation or?
Yeah, in a
because
few
I would
places.
guess that it would make a lot of sense to have an approximation, right? Since we are the probability.
I'll talk about it in 2 slides, and then let's see if you're happy with the answer. Yeah, and we'll talk a little bit later about sampling. Yeah, but feel free to ask later if I don't address your question.
In spite of all these models being intractable, they are very much used in practice.
Yeah, that's true. They're very often used because all of them really like to sample new images, which is kind of what we're all doing now. We're kind of pretending that just generating more images is like solving everything. And it's interesting, right? But yeah. So we'll talk later about if you are able to compute tractably things like marginals, what more can you do with this? So hopefully that will also become clear later. It's like, what's the point of wanting to do more? Why do we even care about these queries? Yeah. So again, hopefully soon you will be given the answer.
So I guess that all the models that you're describing are tractable to sample.
Yes.
That's
Yeah.
the base point.
Sampling is tractable on all of these. Correct. Okay, great questions. I like to get the signal that you're following along. Okay, back in the time machine, back to graphical models. So I guess many of you are familiar. We have nodes that represent random variables. These edges represent dependencies in the distribution. And there's a lot of classic algorithms, based on recursive conditioning, variable elimination, message passing, that will compute for you the probability of some marginal in these types of models. So this has been studied very extensively. But unfortunately, it's also not tractable, right? It's well known that computing a marginal probability on the Bayesian network is sharply hard, right? So that's a very kind of classic result. And then already maybe to your question, approximating a marginal or a conditional is also hard, right? So within a relative error of 2 to the n 1 minus epsilon for any fixed epsilon is NP hard. And so what we're really using these models for when we're sampling is we're just hoping that somehow they are well behaved by accident, and on average they get us something reasonable. And very many applications that use sampling or message passing, they really just hope that giving some answer is better than giving no answer, and you can build something around it, but there's really no guarantee whatsoever that the numbers you get out of these algorithms at all correspond to the truth. Right?
You haven't defined CON yet, have you?
Oh, this was marginals, and this was conditional probability. I very quickly skipped over these conditional queries here. Yeah, sorry. Other questions? So yeah, approximations are not necessarily quickly giving us a solution here when we have these intractable models. But of course, I think you all know about tree width, right? How tree-like is this graphical model? And so tree width is, of course, this parameter that if we fix it, then we can actually compute marginals efficiently. And it's a fixed parameter tractable in tree width. So a very natural thing to do, and I guess this community kind of knows this, right? I don't really have to go into this. But what's very natural to do is to say then, well, instead of considering all graphical models, let's just only deal with ones that have small tree width. So then we have a distribution on which we can really query whatever we want. And that's turning out to be a very fruitful idea, especially in things like computational biology for genomic sequences and so on. But also in just machine learning, where there's plenty of proposals of let's look at the data and let's extract from the data something like a polytree, a thin junction tree, and so on. Just learn a distribution that has, by design, low tree width. And so in practice, that means that tree width can be up to 20 and it runs, and higher than that, it won't run. And it kind of works. It's a tractable model. Okay. So tree distribution, slightly more in detail, looks like this. It's essentially a Bayesian network where every variable has exactly one parent. So it factorizes in this particular way as a product of variables given their parent. And everything runs in time linear in the number of random variables. And what's really neat is even if you want to learn these models from data, you want to compute the maximum likelihood tree-shaped graphical model given some data, the classic Chaulu tree algorithm, which is ancient, will actually do this also efficiently for you. Okay, so it's a very beautiful class of distributions, and it's tractable for all of these things. Question?
Yeah, Guy, is a naive Bayes a particular case of a tree distribution?
Yes. Yeah. So in naive Bayes, every variable has one parent or zero. Yeah. Yeah. But yeah, exactly.
Is this Chaulu algorithm basically the same as Yanakaki's?
So the Chaulu tree algorithm is finding a maximal spanning tree in the mutual information graph of the data between variables. And this is provably giving you the optimal tree-shaped graphical model. Yeah. So it's different from Yanakaki's, which I guess is the database equivalent of the variable elimination algorithm for graphical models. Okay. Okay, so there's an issue though. We actually lost something. All of these models we had previously, they can capture distributions over images of cats and dogs that are very complicated. They can even capture distributions over natural language. But our tree-shaped graphical model has a much harder time with this. Because we kind of restricted the dependencies to be only from one variable to the next, everything has one parent, we somehow lose the ability to represent all the distributions. We no longer have a class of models that can represent everything. But there's also a solution for this problem in AI machine learning, which is just build mixtures. If you build mixtures of things, you can fit anything. Okay. So let's take, for example, two Gaussians and create a mixture of two Gaussians. It looks like this, right? Some convex combinations of simpler distributions. And we can still compute our likelihood, marginals, conditional probabilities. We just have to do so in every single component of our mixture and then kind of average the result. So this is a nice, cheap way of getting good results. And we'll actually heavily use this idea when we build probabilistic circuits. It's very convenient to actually think of these mixture models as actually having a hidden variable z, a latent variable, that tells you which of the two components we are drawing a sample from. Okay? So when you get a mixture of two Gaussians, implicitly in there is some categorical random variable that tells you which of the Gaussians does my data come from. Okay? That's really just capturing this weight here. All right? This is kind of choosing, it's flipping a coin and choosing which of my Gaussians am I going to get my data from. Yeah?
So convex means linear and positive weight.
Yeah. Yeah. And so we'll later on actually use the fact that you can make explicit these latent variables, and they will tell us something about query tractability later on. Okay, so we have increased expressiveness, but unfortunately, well, you can prove that in the limit of infinitely many components in your mixture, you can do whatever you want. So that's nice. Okay, it's fully expressive. But what we really care about is not expressiveness. We don't really care, with infinitely many parameters can we fit this data. The question is with some finite amount of, it could be millions or billions, but it's still a finite number of parameters. Can we actually fit all text on the internet? Okay. And so that's a different story. So that's not really a story of expressiveness, but what machine learners would call perhaps expressive efficiency, and what logicians would perhaps call succinctness. So this is the question of how compactly can we represent complicated distributions, okay? And so here I would like to intuitively argue that, even though a mixture of Gaussians is very expressive, in the limits, it's perfectly expressive. In the finite, it's kind of a useless thing. For example, let's say we want to have a mixture of Gaussians that represents any of these 4 different distributions. Then this is what we get if we have a mixture of 2 Gaussians. It doesn't really look great, right? These are the 2 Gaussians. I think here we have maybe 10 Gaussians. Not really a very good approximation. Here I think we have 100 Gaussians, and here it starts to look okay, but barely, right? And so the problem here is you just need a massive, massive number of components in your mixture to actually have this expressiveness in practice. It's not very expressive efficient. Okay. Yeah.
But classical machine learning learning theory would tell you that you don't want to fit every piece of text in the internet, right?
Yeah.
What is the trade-off between regularization and expressiveness here?
That's a very good question, which I was not planning to get into, which is the very end of the tutorial. But yeah, so having the capacity somewhat limited actually does help you be more robust sometimes intuitively. The reason why in practice, even when you learn like a mixture of 100 Gaussians from data, it doesn't work, is just because actually optimizing this marginal likelihood landscape is impossible. It's highly multimodal. So even though in theory, yeah, so this also doesn't work. And then, okay, even though this is a good regularizer, it's probably not good enough to capture all the text on the internet. So you kind of lose either way. That's the short answer. Okay. Are there more questions?
Yes. So getting back to the theory one, if I think about a finite distribution, n random variables, they're all binary. How many mixtures of, I don't know, tree-like Bayesian networks do I need to represent an arbitrary distribution?
That's a good question. My guess would be if you have n random variables, 2 to the n minus 1. Yeah, I think so, because you can always construct. Well, okay, someone could probably prove this over the lunch break, not me. Maybe you can, but you can probably construct a probability table where the numbers are somehow different enough that they can not be generated by convex combinations of things and whatever. So I think you'll solve that problem very quickly. Yeah. Yeah. Okay. Good question. So yeah, maybe there's a problem in here worth studying. Okay, so mixtures are tractable, but we have this caveat. Okay. Let's make the problem even harder. I would like to know which combination of roads is most likely to be jammed on Monday at 9 a.m. So here we have something called map inference. We have some observed values for our random variables. We have a question of what is the most likely state of all the other random variables. Okay, all of the other ones. This is also an interesting query class, and we'll talk about it later as we find a model for that is tractable for this query class. Yeah, this is just writing the same thing, right? We have query and evidence, and together they form the set of all random variables. Okay, so unfortunately, even if we have a mixture of Gaussians, or let's say a naive Bayes classifier where the class is a latent variable, or any kind of mixture of trees, computing this is also intractable. The reason is that these mixture models, implicitly, they have this hidden variable z that tells us which of the components of the mixture am I actually drawing from. And implicitly, we're actually marginalizing out that variable. And so the max of the sum is not the same as the sum of the max. And so we cannot really solve this maximization problem in each of the components separately and then somehow aggregate the result, because that's not correct. Okay. And so now we have a slightly harder query, which is intractable for even mixture models. Again, if you want to look at applications, here's a slide where you can find some fun things to do with map inference. Specifically, you can find the most likely completion of an image that you only partially observe. That's a fun thing to do. All right, so for map inference, all of these things were already intractable. For mixtures, you cannot do it because this latent variable you cannot really deal with. On a tree-shaped graphical model, you can still compute your map inference. Okay. So we're pushing the picture forward, and we're seeing that there's actually quite some interesting properties here. Okay, let's make the problem harder. Let's say I want to know which combination of roads is most likely to be jammed at 9 a.m. regardless of the day. Okay, I don't really care about Monday specifically. So now we have almost the same query, except I'm implicitly summing over all days of the week. I don't really care which day of the week it is. So now we again have this problem where we have the max of a sum, which is not the same as the sum of a max, and we cannot possibly compute this. And it's you can prove that this is intractable, and folks have done so. So on a general graphical model, this is NP to the PP complete. Even on a tree, this is NP hard. Even on naive Bayes, this is NP hard. Okay, just marginalizing out a few variables. Make sense?
Is there an intuition why it's hard on a tree? Just some intuition.
It's been a while since I read these papers, but there's some kind of subset sum-like problem that you can solve here. I forgot the details. Do you remember, Eugen? Or maybe Dennis remembers.
To max set reduction.
Yeah, I don't recall, but yeah, we can look it up for you. The pointers are also here. Okay, marginal map, very difficult. Even though it's in English, it looks like a very natural type of query to ask in your distribution. All right, so this is the picture. Nothing's tractable right here. And there's actually many more query classes that we'll consider today. So we already talked about this one, which is way more complicated than what we already discussed, right? It's somehow the combination of this map inference, finding the most likely value, with marginalization over events that are defined in logic. So Eugen will talk about those types of queries. You can have query classes that ask, are there more traffic jams in Westwood than Hollywood? Like essentially looking at counts among sets of random variables. So this is kind of like comparing aggregate queries, or I don't know how you want to think of this. So we'll talk about languages that can solve these types of queries. Is traffic more uncertain on weekdays? So Eugen will spend quite a lot of time talking about information theoretic queries, computing things like entropy, scale divergences between distributions efficiently in time linear in the size of the distribution's representation. And then Eugen will also talk about, for example, this type of question: what's the causal effect of doing roadworks? Causal backdoor estimation, causal effect estimation, where you also are given a distribution plus some causal assumptions about what causes what. And then you want to know what's the effect of a certain operation if I do it on my distribution, okay? And so these are all way more complicated than anything I already showed you, and so we'll cover, hopefully, all that ground. There's one distribution, however, that is tractable for anything you could possibly want to do. Any advanced query, marginal map, whatever. There's one distribution that's always tractable, and it's this one. It's the fully factorized model. So if I have a graphical model where nothing depends on anything, I just have a product of univariate simple distributions, then I can compute whatever I want. I can compute evidence, marginal map, and so on. But obviously, this is a dumb thing to do because this is not the real world. In the real world, things depend on each other. However, I'm not showing you this slide to be annoying. The idea of representing distributions through factorization will actually also be a key ingredient in the more advanced models we talk about later. So the idea is important. This particular implementation is ridiculously dumb, and you would never want to do it, but it does give you tractability. Okay. All right. Okay, so overview of this part of the talk. We have these two dimensions. We have things that are very expressive efficient and not very expressive efficient. We have things that are very tractable, very intractable. And hopefully I convinced you that most of the popular kind of deep learning ways of representing a distribution are very expressive. The internet can be captured, but not much you can do with them. Usually you can just sample. Sometimes you can compute a likelihood. Okay. On the other hand, we have our favorite classical AI things like naive Bayes, a fully factorized distribution, tree-shaped graphical models, simple mixtures of Gaussians. They are very inexpressive, but very tractable. And of course, where we want to be is somewhere here in this sweet spot in the top right corner. And so that will be the topic of the next part. All right, have I answered these questions for you? What are probabilistic queries, and are the current models tractable? So I hope I did so. And for the next 20 minutes, 22 minutes. Yeah, so by the way, I should mention, we haven't really partitioned these 8 questions into like perfect, 4 times 1 hour slots. So we will try to take a break, possibly in the middle of a story, but hopefully you'll be then enticed to come back for the next part. Okay. So hopefully you're convinced about this first bullet point here. So let's now talk about probabilistic circuits and why they are tractable for these queries. All right, so the goal here is to given some class of queries or reasoning tasks, can we design some expressive models that are tractable for it? And because we're in the age of deep learning, we would like these to be somehow similar to your neural networks. We want them to be computation graphs that are deep and expressive. Okay. Already showed you this. And so these circuits that we'll talk about, they will kind of live in this corner. And there's kind of two ways to achieve this. One is to start simple. Take your tractable model that's very inexpressive and try to somehow over-parameterize it. Try to have, give it, 500 million parameters and then hope that it becomes rich enough to capture interesting things. So that's one way to go. And in some sense, that's kind of what we're doing. But in another sense, what we're going to do is also just take these deep learning models and impose some structure on them. Structure that allows us to compute things efficiently. All right, so let's start simple. So we're going to build computation graphs, and the base case of a circuit or a computation graph is an input distribution. Okay, and so here we'll consider some arbitrary set of inputs like Gaussians, for example, and we can also consider things like indicator variables, right? So if you're a logician, you can think of this as being a very simple distribution. It gives 100% probability to X being false. Okay. So if you're a logician, please just think of these as literals. And we will assume that we can do a few things with these very base case elements. We'll assume that whatever query we're interested in, you can always compute it on these atomic forms, right? We can ask a Gaussian, what's the probability density of 1.3? It happens to be this probability density. We can ask it, what's the marginal, which if you have a single random variable is basically asking to give us 1, which is the normalized distribution sum over all probabilities. Or if you want to deal with unnormalized distributions, this would be called the partition function. Don't worry about it. We can ask Gaussian, give us your most likely state, give us the mode of this distribution. So all of these basic things we assume we can ask. Okay. Of course, we can also ask these of a logical literal. These are also easy to ask there. Okay, so now we have things like Gaussians or literals, and we need to somehow combine them into a more complicated computation graph. And we already know how to do that, to take something that's inexpressive and make it more expressive, which is the idea of mixture models. And so here we have a Gaussian mixture model that I showed you earlier. And we will now just represent exactly the same thing as a circuit. So there will be some variable x1, which is the input to our circuit. We give it to the first Gaussian and the second Gaussian, and then we kind of mix the result together. Okay. And now if I want to compute something like the probability of a particular value, I say, what's the probability density of 5 in my mixture of Gaussians? First component says 0.06, second one says 0.21. We create a mixture of them, so we average these out, and we get for the mixture of Gaussians, a likelihood density of 0.09. Okay, so it's just a simple feed-forward computation that gets us the probability of a particular value. For the rest of the tutorial, I'm going to skip kind of this part here. I'm just going to give you these base case distributions, and all of them will be annotated with some scope, which is which random variable are we talking about. So both of these Gaussians are talking about random variable x1. All right. So hopefully that notation won't be too confusing. And I won't really put these arrows everywhere. So these are circuits that kind of do the feed-forward computation in a natural way. All right. So now we have mixtures of Gaussians, but we only have a single random variable. Okay. Ideally, we would like to have a very high-dimensional distribution, meaning 1 over many thousands of random variables. So how do we take a distribution over 1 variable and make it a distribution over 2 variables? Well, we multiply the distributions. We do this idea of factorization, which was the ridiculous thing I showed you earlier. But it does allow you to expand the scope of your distribution to multiple random variables. Okay. And so here, for example, we could have a joint distribution over 3 random variables. That is the product of independent Gaussians. And so this is kind of like a diagonal covariance matrix, multidimensional Gaussian. Okay. A very simple idea, but it does give us some extra power. And we'll, of course, represent this operation of factorization using a product node And so this is now our little product of essentially a three-dimensional Gaussian. Okay. Yeah.
So the covariance is black. There's no covariance because they're independent.
Yeah. So this basically means there's independence between the three random variables in the very simple multivariate Gaussian. Okay. Again, if I'm given some data point where I know the value of x1, x2, and x3, I can ask each of these Gaussians, how likely are these values, and I can multiply them to get the likelihood under this factorized model. It should be pretty straightforward. All right. And now we just have to make a little bit of an inductive leap where we say, let's just do this recursively. Right? We have our input distributions, Gaussians. We have our mixtures of things. We have our factorizations of things. And now we just built, mixtures of factorizations of mixtures of factorizations. And we end up with a circuit language that looks like this. Okay? That makes sense for you? I mean, this is a natural thing for most people here, I guess. All right, so this is nice. And you can also do this in code. If you like to just program things instead of prove theorems, you can play with actually building these things. Yeah.
In the implementation, you probably will need a kind of a relational representation of the circuit somehow. You can really store pointers, so it becomes kind of a whole.
Yes.
So if you have to define a query language over representation, what does it look like this, or more like?
Yeah, so depending on which framework you use, the representation of this circuit will be different. I think here it's really just like, okay, at the CPU you just have pointers. On the GPU you end up with some kind of sparse matrix format, which is when you get interested, of course, where you would, essentially. So what we tend to do is actually layer the circuits, have like a different matrix for every layer, so we can on the GPU easily compute queries. But there's a few design choices you can make. Yeah, but you're right. To actually represent like a circuit with like 500 million edges is like a non-trivial systems engineering problem. Yeah.
Can you go back one slide? Yes. So I'm trying to understand here the conceptual framework. So if I look at the variables x1, x2, x3, and 4, and so on, you started with them as being independent random variables.
Mm-hmm. Right. So here they're independent.
No, but they're right at the end there. Aren't they independent?
So x1 is in this circuit. No, so nothing is independent of anything, because as soon as you create a mixture of two things, even though variables are independent in the component, they're no longer independent in the mixture. I don't know if that's intuitive to see. But yeah, mixtures basically break all independencies that could exist in their components.
But you start with the independent distributions.
Yes. Yeah. So every product here is expressing some independence between the inputs, but it immediately gets broken by the mixture you put on top of it. Yeah.
I see. So you're adding two distributions. They might have been independent, but once you add them, they are. Okay.
I mean, maybe I can make this more intuitive for you by saying, let's consider a naive Bayes model, right? So in naive Bayes, given the class variable, the root, all of the features, the leaves, are independent. Okay. But in the joint distribution, where you marginalize over all classes, the features are not independent because some features tend to co-occur more often in certain classes, right? And so that's how the dependency comes into the picture.
Thank you.
I think I can make a parallel to query evaluation policy databases where the input tuples are independent, but once you do the query, if you look at the result, you get all these mixtures.
Right. Yeah. Given the query, the tuples are no longer independent. Yeah. Okay. Great question. Yeah.
Yeah. So on the next slide, the expression that you show, technically this is a tree rather than a circuit when you unpack it like
this. So you'd have to create a local variable for some of these circuits to reuse them. Yeah. This happens to be just one DSL. There's a few others. Yeah. Okay.
So do you gain anything by removing this? So in the product node, everything is independent, right?
Yeah.
Suppose you add some tiny bit of dependency, let's say you impose or whatever. Do you gain anything or lose anything?
That's a good question. At some point, we were doing some research on exactly this. Can we somehow generalize the independent product and still be tractable? And we found a way to do it. I would have to check my notes to recall how it works. But then we couldn't really get the model to train in a way where we could convince machine learners that the added expressiveness actually helps you fit data better. So I think that project kind of got stuck. But we should revisit since if you're interested. Yeah. Okay. Question?
Can you make a historical note here to say like how long ago have these some product networks become interesting?
Yeah. So in the afternoon, I have a bunch of slides kind of connecting, what is actually this alphabet soup and what's in it, right? Arguably, all of the classical graphical models that do some product inference, like hidden Markov models, Chowdhury trees, they're all instances of this, and we'll talk about that later. So in that case, it goes back to 1968 or even earlier.
This incarnation.
The graph representation, I would say, mostly, so people I think were doing BDD-based probabilistic inference in the late 90s, but mostly with arithmetic circuits in 99. This kind of circuit representation was, I guess, popularized most. And at the same time, there were things like and/or graphs, Marina Dechter's group, which are also a form of circuit in a different syntax. So there's been a lot of work. Manfred Jäger introduced probabilistic decision graphs in 2005. Pedro Domingos introduced some product networks in 2011. So there have been lots of alphabet soup acronyms that kind of all are the same rough kind of circuit-based probabilistic model idea. Yeah. Happy to mention others if you, yeah.
Can you please go to the previous slide? So my understanding of circuits is that these variables provide the input, and then you do some computations through this. But I mean, you have the same variable labels.
Yes. How is it possible that we have two random variables with the same name? That's your question?
Yeah, exactly.
Yeah, very good.
This confuses
Yeah.
me.
So the simplest case is to look at here. Why do we have two random variables x1? Because we have a mixture of two Gaussians, and both of these Gaussians are talking about the same random variable x1. Yeah, but it's counterintuitive if you see it as a graph, like why are two of the inputs the same? They're essentially two different base distributions on the same random variable that you mix together somehow. Yeah. Okay, good. So how do you evaluate these things? Let's say you want to compute the probability of a specific feature vector. Then we ask all of the little Gaussians in this probabilistic circuit, what's the probability density of these values? They all have their own opinion about what that should be. And specifically, even if you have x4, the same random variable, these two different Gaussians will have two different probability densities for that random variable. Then we just have factorizations of mixtures recursively. So we take sums of products, and we end up with, in this entire very complex distribution, a density of 0.75. So the probability of a complete data point is just this feed-forward evaluation. Okay, should be straightforward, hopefully. We're going to make this much more complicated soon. All right, so is this it? We just take sums of products, and we have essentially a neural network with many layers, and that's it. No, it's a little bit more complicated. We'll actually have to study certain properties of this structure in order to compute anything that's more complicated than just a likelihood. Okay, and so that's the next part, but I feel like maybe we should leave that for after the break.
You still have 7 minutes, stop you. Okay.
Dan has so much authority that I feel like I cannot. All right, so I'll already introduce as much as I can. And I do so poorly because I'm tired after an hour. The first property we care about is decomposability. And I'll just spend 7 minutes talking about decomposability. So the idea is that in a factorization, you're not really allowed to multiply some probability of the height of a person with the probability of the height of a person. Like you need to multiply things that are different random variables. Otherwise, it doesn't make sense. You don't want to get probability square in your units. Okay, so that's essentially the idea of decomposability. Is whenever we have a factorization, the random variables have to be different from each other. Okay, so if you think of it as a factorization, this is a super intuitive concept. I will get to this later, but theory people may recognize this as syntactic multilinearity. Is anyone nodding? Syntactic multilinearity is what Yeah. Yeah.
What do you mean?
That's not what I mean, but that's also related. Yeah.
Oh, okay. Oh, so you just mean within each product there's only one?
Yeah, every local node has the fact that what it's multiplying does not share any variables. So I think in arithmetic circuit lower bounds, you would call this syntactic multilinearity, as far as I know. Okay, this is a non-decomposable circuit. You're multiplying two Gaussians that both talk about the same random variable. Doesn't make sense, it's not allowed. Okay, second property, smoothness is also super intuitive. If you think of sums as being mixtures, then this is saying when I build a mixture of two Gaussians, I always mix together the same random variable, right? I want to have a more complicated distribution over, let's say, the age of people in Berkeley. I'm not allowed to create a mixture between the age of people in Berkeley and the temperature of the sun. Like, those are different things. You cannot mix them together in one distribution. And so that's really just what smoothness says. Mixtures are always over identically scoped distributions. This is a non-smooth circuit where somehow we violate this constraint. So decomposability is an interesting property because getting decomposability in your circuit is a somewhat non-trivial thing. If you start from some other representation, like getting decomposability is a hard problem. Smoothness is very easy. If you give me a circuit that's not smooth, I can always make it smooth by just adding a few extra dummy random variables. So this is kind of a boring property, but we'll assume it because it makes all the algorithms easier.
What does it mean? What does a non-smooth circuit mean?
I mean, you could still somehow say that whatever variable is not being used is somehow not part of the likelihood computation, and it still defines somehow a distribution. It just doesn't really make sense because it's kind of leaving some, it's multiplying by one, which is an unnormalized distribution. You can give it semantics, but it's not pretty. So let's not go there.
So I guess the semantics is part of how you enforce it. Can you maybe, is it easy to explain how to enforce smoothness on this?
Yes. So if I want smoothness here, I would basically add a multiplication with a sum node of that basically gives a uniform distribution over x1's values. Here, so I'm basically saying implicitly, if I'm missing a variable here in the mixture, it means that I'm multiplying by 1, which is the no up. And so multiplying by 1 means that for this variable, I have a uniform distribution, moreover, one that's unnormalized, that's just 1 everywhere. That's how smoothing works. If you want to give semantics to this thing, that's how smoothing works.
Would it be fair to just sum the weight of W1 and W2 in this? Like if you had, let's say, 3 of them, could you sum the weights and these weights not multipliers?
Yes, so you would still multiply whatever variable is missing here. The 1 will still be multiplied by the same W1.
Yeah, but if there's 2 copies of X1, could you just change the weight of W1 to W2?
No, because these are different Gaussians with different means and standard deviations. You cannot just, if they were the same distribution, you would basically get rid of it.
They're both referred to as X1.
They are the same random variable. The scope is X1, but they're different parameterizations of the distribution over X1. Yeah, that's a very important point. Yeah, of course, if they were the same Gaussian, you would just replace the whole thing by a Gaussian, by that one Gaussian. Yeah.
So maybe, yeah. I mean, why do you insist on Gaussians? I mean, why do you insist on your basic blocks to be Gaussians? Is it important? Is it just an example?
Oh, this is just because machine learners like to see this particular curve. But think of these as Boolean literals, if you like. This is some coin flip for X1. This is another coin flip for X1 with a different bias. It doesn't really matter. It's whatever you like it to be. Some very simple distribution.
My question was, what property of the probability distribution are you going to use, if any?
So the only thing we'll assume,
my own continuous distribution.
The only thing we assume here is that once we have a single input distribution, we can compute whatever we want, a marginal, a likelihood, a mode. We assume these to be tractable, atomic things. Yeah.
So here you define smoothness only for plus gates that receives directly inputs.
Yes.
So what's the general definition?
The general definition is whatever is below here, it has a scope. It's a set of random variables that is being represented by that distribution. The scopes have to be the same, even if there's multiple variables in the scope.
The same set of variables.
The same variable sets. Yeah.
Yeah. So can we go back to the previous slide? In undirected BGMs, it's quite common, let's say, to represent a distribution over 3 variables as a product of 2 factors, 1 over x1, x2, and another factor over x2, x3.
Right.
So is that not allowed as...
That is not decomposable because those share variables, of course. Typically, factors in a factor graph share variables. So that's not decomposable, which means it's really not a factorization of independent things. you're actually multiplying conditional probabilities, or so that's not what we're talking about here.
I see.
And that's also an intractable model for that, exactly that reason.
Yeah.
So what I will tell you after the break is with these two simple properties, which are totally intuitive, I hope, you can compute tractable marginals on whatever circuit you like, however big it is in time, linear in the number of edges. So hopefully you'll come back for that after the break.
And if you lift any of these conditions, then you can.
You cannot. Well, smoothness you can always get back with a simple operation. Decomposability is necessary. Yeah. Eugene will talk about this kind of is it a necessary condition problem this afternoon. All right, thank you.
Okay, let's thank Guy. So let's take a couple of minutes for questions, if there are any questions. Oh, plenty of them. So Hank, let's start from the back.
So in the spirit of semi-rings, if we replace some important with semi-rings.
Yes, so as soon as I'm done with my part, Eugene will tell you exactly how it generalizes to any semi-ring, including Boolean. Yeah.
Yes,
has people studied the query languages over these probabilistic circuits as well?
This is what we'll hopefully do the next 2 hours, is tell you how to compute entropy, scale divergences, marginals, map inference, causal effects, all of those.
No, yeah.
You don't think of those as query languages. What do you think of as a query language?
Something that allows you to define these queries in a general way, right?
Yeah, so we'll talk a little bit about an actual query language, which is how do we compose products, logs, integrals. Like there will be a little language in Eugene's part. But yeah, let's think of an interesting language to define and see if it's tractable. And in fact, actually the causality work, which is actually Benji's work, I don't see him, is also about you're given a graph, which is your causal assumptions, which you can think of as the query language. And now can I compute the causal effects on my distribution? So there are, later the queries will become more structured and they will start to look more like an actual language rather than just values for variables. Yeah.
So Uri, please.
So can you explain again where the dependencies start to show up? Why can't you just take all the part of the network which is labeled by x1 and that gives you x1?
Yeah. A simple example is, okay, let's come up with some really dumb example on the spot. Let's say that my location is Berkeley, then it's very likely that, I don't know, the weather is nice and there are smart people around. Okay, so and let's say that these are independent variables. Okay, if I'm in, I don't know, I shouldn't have said smart people because no one has to find non-smart people. Let's say the weather is nice and some other variable. They're independent, but they're very likely to be true in Berkeley. Okay, let's say now I'm in Belgium. I have two other random. I have the same random variables, and they're also independent of each other, but they're likely to be not the case. They're independent but biased to be unlikely. Now, if you don't know where you are, and I tell you the first variable is set to true, you're more likely to be in Berkeley, which means the second variable is also more likely to be true. Even though in Berkeley they're independent, in Belgium they're independent, in the mixture they depend on each other. Does that make sense?
But where do you see it in the circuit? I mean, why can't I do what I said to try to get independent parts for x1, x2, and then everything seems to be independent.
I'm not sure that, so yes, you could somehow turn this into.
So if you look at the subnetwork, just composed of everything which is labeled by x1.
Yeah.
So this would give you some random variable.
Yeah, this would give you what's called a marginal distribution on x1. So you can do that. Yeah.
Now just do the same for x2.
Yeah, you get another marginal distribution over x2. But you can do this for any distribution. I can always take a distribution where things depend on each other and get two marginal distributions.
But why isn't that the distribution that you are getting?
Because for the kind of Berkeley, Belgium example, the mixture actually makes things depend on each other. If I know that in one of these mixture components, something is more likely, everything becomes more likely in that mixture component.
No, so what is the definition of it? What is the exact definition of plus?
Plus, okay, it's exactly this. It's just a classic mixture model. We compute the probability in both components and we average it.
Yeah, but here it's the same random variable. So they're both labeled x1.
Oh yeah, if I have multiple random variables, this just becomes a vector of random variables and a vector of random variables.
May I suggest that we continue this during the break because people are looking for coffee?
Okay.
So let's thank Guy once more. And,
Yeah, I should bring a video.